Hello everyone, you're all welcome to this video. I remain your tutor, Mr. Life Changer. And in this video, I want to be solving waec past question, chemistry paper 2022. Okay, there should be a chemistry here, 2022. Okay, so these are theory questions. Okay, so I like you to follow through and hopefully you're going to learn a lot. Now the first one says we should define ionization, first ionization energy of an element. Now the first ionization energy is the energy that is needed or that is required to remove the first electron from an atom. Okay, so not just any electron but the valence electron. Okay, valence electron means electron in the outermost shell. Let's assume you have a nucleus inside here. This is a valence electron. The energy required to remove it is what we call the first ionization energy. Now the second question here says consider the following table and use it to answer the question that follows. Okay, so we have a table, we have elements, we have atomic numbers, and we have first ionization energies. Okay, that is good. Now it says that B is less than BE despite the fact that the atomic number of B is greater than that of BE. Okay, now this is quite easy because now ionization energy is meant to increase across the period. You can look out for my video on periodic table. I explained this. So you can see from 520, 900, but there is a decrease here. Then it continue increasing 1084, 1004. Then there is a decrease here. Then it continues increasing here. Are you seeing that? Now at that point where they decrease, just like here, has something in common. Now whenever you see a dive in the first ionization energy, it is simply because of the stability of the element before it. What I mean is, for example, if you see the configuration of beryllium, beryllium is in number 4. The configuration is 1s2, 2s2, meaning that all the orbitals are completely filled. So it is more stable. It is more difficult to remove an electron from an atom that has stable configuration. So you can see that this is more stable. That's why it is higher than the next. And that's the same thing that is obtainable here in nitrogen. If you notice, nitrogen, from nitrogen to oxygen, there is a decrease. That's because the valency of nitrogen, atomic number of nitrogen is 7. If you write the configuration is 1s2, 2s2, 2p3. So 1s2, that means 1, 2, 2s2, 1, 2. Then 2p3 is like this, 1, 2, 3, which is half filled. So half-filled orbitals and fully filled orbitals are very stable. So half-filled or fully filled. So that is the only exception. So generally, electrons, or will I say, ionization energy is meant to increase as you go across the period from left to right. But there are exceptions, which is at the group 2 elements and also the group 5 elements. And the simple reason is because of their stability. Their configuration is either fully filled or half filled. I hope that makes sense. Now the other one says when titanium chloride was electrolyzed by passing 0.212 amperes current through the solution for 500 seconds. Okay, 0.015 grams of titanium was deposited. What is the charge of titanium ion? Oh, okay. Now for us to know the charge of titanium ion, titanium is a metal. The formula for Faraday, I prefer to use mass over molar mass is equal to Q, or you say IT over NF. Q is the, Q equal to IT. Okay, so N here is the number of charge, the number of electrons, which will represent the charge in the case of metals. So from this question, you can see that the mass of titanium is 0.015, okay, divided by the molar mass of the titanium is given here is 48. Now equal to the current is 0.12 times the time, we are given 500 seconds. Now divided by number of electrons is what we want to find. F is Faraday's constant, which is 96500. You see that? So if we cross multiply, you're going to have N to be equal to 0.12 times 500 times 48. Now divide by you have 0.015 then times 96500. Okay, so let me use my calculator. Permit me to do that quickly. So 0.12 times 500 times 48, now divide by 0.015 times 96500. So I'm getting 1.99 approximately. 1.99, so that's approximately 2. So that means titanium should be written as Ti2 plus in this case. Okay, makes a lot of sense. Now C says aluminum can be obtained by the application of electrolysis. State the electrolyte which yields aluminum on electrolysis. The electrolyte that yields aluminum on electrolysis can be aluminum hydroxide or can be bauxite. You can have Al2O3. Aluminum oxide, is electrolysis of aluminum oxide can give us aluminum in electrolysis. Okay, that is very, very important for us to note. Now, that is very, very important for us to note. Okay. Okay. Give me a second. I seem to be having a bit of an issue here. Okay, so now let's proceed. So I said aluminum oxide, okay, and if you like, you can mix it with cryolite. Mixed with cryolite. I hope that makes sense. If you want to know the formula for cryolite, it is Na3Alf6. Okay, now that's by the way. Now the next one says name two major factors that would favor the sitting of a aluminum smelter in a country. Two factors that the two factors based on this is going to be, number one is going to be the cheap source of electricity. Okay, one of them cheap source. This is just economics of production. One of them is cheap source of electricity. Then the second one is abundant deposit of bauxite. So if the deposit of bauxite is abundant, then we are going to have, a favored aluminum smelting in the country. Okay. Now the next question says define the term paramagnetism. Okay. Paramagnetism is simply the ability of a substance to be influenced by a magnet or to be attracted by a magnet. That is what paramagnetism is. Okay. And in chemistry, the elements, the metals that are paramagnetic are usually transition metals. That's one of the properties of transition metals. Now the other one says consider the following ion, this and this. Deduce the number of unpaired electrons in each ion. Now we cannot tell the number of unpaired electrons except we have written out the electronic configuration. For example, the first one here, chromium 24 is 1s2. Okay, you can write argon, which is 18. Okay, then the next one should be 4s and 3d. So 24 minus 18 is 6. So I'm going to share 6 electrons here, meaning that 5 is going to come here and 1 is going to come here, because this is half filled is stable, so you half filled before you fill this. That's how it's done. Okay, so now, but if you say Cr2 plus, it means that 2 electrons will be lost. I'm going to have Cr24. 2 plus is going to be argon. Please watch this. And here is now going to be 4s0. And here is going to be 3d4. So if I want to, d has up to 5 orbitals. So 3d4 means 1, 2, 3, 4. So here you see there are 4 unpaired electrons. Very easy, right? 4 unpaired electrons. Now in the case of Cr6 plus 24, in the case of this, it means that 6 electrons has been lost. So if you lose the whole of the 6 electrons, you are going to be left with Ar, which is 18, and this will be 4s0, this will be 3d0. So there will be no unpaired electron because this is completely filled. So no unpaired electrons. Now I want to say this, that you can use argon. Argon simply means 1s2, 2s2, 2p6, 3s2, and 3p6. Okay, so whenever you are naming a transition element, you don't need to list all of this. You can just use argon in a bracket this way, then you complete the rest. All together is 18. 2 plus 2, 4, 4 plus 6, 10, 10 plus 2, 12, 12 plus 6, 18. I hope that makes sense. Okay, so let's go to the second question. The second question here says, number 2, it says, define the term Avogadro's number. Okay, Avogadro's number is the number of substance that makes up 1 mole of that substance. That's what Avogadro's number is. The number of substance that makes up 1 mole of a substance. I hope that makes sense. The number of substance that makes up 1 mole of a substance. That is Avogadro's number. Now, and the number, you can also write the number. It is 6.02 times 10 raised to the power 23 of that substance. That means 1 mole of a substance must contain, that substance can be ion, can be molecules, can be atoms, would contain 6.02 times 10 raised to the power 23 of that substance. Now the next question says, if 2.30 gram of an oxide of nitrogen X contains these molecules, calculate the molar mass of X. It's quite easy because you can use the formula mass over molar mass is equal to number of atoms over Avogadro's constant. Very easy. In the case of volume, you can also say mass over molar mass is equal to volume over molar volume. Quite easy. So the mass here is 2.030. The molar mass here is what we are looking for, so we'll just say X equal to the number of atoms. Here is the number of molecules, is 3.01 times 10 raised to the power 22 divided by the Avogadro's constant is 6.02 times 10 raised to the power 23. So this will be 2.30 divided by X is equal to, okay, we already have it here, is equal to this is 0.05. So that means X is going to be 2.30 divided by 0.05. Let me use my calculator here quickly. And that is going to give us 46. So the answer is 46. Okay, so that oxide of oxygen is 46. So the next question says, deduce the formula of X. That's quite easy because nitrogen is already 14. 14, let me say plus M equal to 46. Okay, and since it's oxide, you know that the molar mass of oxygen is 32. So let me say M will be 46 minus 14, which is 32. Okay, so that's oxygen. So it means that the oxide is NO2. Okay, that means nitrogen plus, because oxygen is 16 times 2 makes it 32. Can you see that after subtracting 4? So the answer to this question is NO2. NO2. Quite easy. Now the next one says, describe briefly what happens when each of the following substances are added to water. Now this one is not going to dissolve, it's not soluble in water. is a complete organic compound. Carbon chloride is an organic compound. Are you with me? Carbon chloride is an organic compound. Then silicon chloride definitely is soluble in water because it is polar. Okay? And remember, as a general rule, a polar solvent will always dissolve in a polar solvent. A non-polar solvent will dissolve in a non-polar solvent. Okay? So this guy here is non-polar, so cannot dissolve in water, but this one here is polar and can dissolve in water. Quite interesting. Now explain briefly why the reactions in AI, BI, okay. That looks like there is a problem with that question. Okay. I think I missed it. I missed out a question here. We can always do that later. So let's see the next question here, which is C. C says, study the diagram below and answer the question that follow. I says, what is the setup used for? If you look at this, this is exactly the setup for electroplating. Yeah, for electroplating, right? Where actually it can also be used for purification of metal. Yes, once you see two metals, you know that it has to either be electroplating or purification of metals. That's how it's done. Okay, very important, especially seeing that one looks a little rough, and that's important for you to note. Now the next one says, mention two compounds that can be used as electrolyte in the cell. Now this, anytime electrolysis is used for electroplating or purification of metal, two conditions you must note. The first condition is that the anode must be a metal that is lower than hydrogen in the electrochemical series. That means the anode can be copper, can be silver, can be gold, can be mercury. Any element that is lower than hydrogen in the electrochemical series will be the anode. Then now, when we come to talk of the electrolyte, for the electrolyte here, we are going to use the salt of any of these metals will be used as electrolyte. If I use copper as anode, then the electrolyte can be copper sulfate. It can even be copper nitrate, any salt of copper. Silver, we can have silver nitrate. Gold, we can have gold nitrate, and so on and so forth. That's important for you to know. Now the next one says, write a half cell equation for the reaction at the anode. Now during this process, this is a special case of electrolysis, how electrodes affect the product of electrolysis. And in this case here, there are only two reactions. At the anode dissolves. At the cathode, the metal accumulates. So at the anode, we said that metal dissolves. So you're going to have something like this. If I want to use copper, for example, I can say copper would give me copper ion then plus 2 electrons. This is what happens at the anode. The anode dissolves. The copper dissolves to become copper ion and releases electron. Then at the cathode, the metal accumulates. Metal accumulates. Accumulates means that the metal, starts loading. So you're going to have the reverse of this reaction, which is the ion there takes up electrons and be deposited as metal. So the metal will leave one end and will go to the other end and be deposited. Then this is only possible if the anode is a metal that is lower than hydrogen in the electrochemical series and the electrolyte is a solution of its salt. Please do not forget that. Now the next question says here that calculate the electrochemical equivalent of copper if the cathode gains mass of 3.2 grams, where 50 amperes of current was passed for 15 minutes 13 seconds. Okay, and we are asked to calculate the electrochemical equivalent. Now you should know that mass deposited is equal to ZIT, where Z is the electrochemical equivalent. So your Z now is going to be mass divided by IT. Now the mass here is 3.2. The current here is 50 amperes. Multiplied by the time is 15 minutes 13 seconds. 15 minutes 13 seconds means 5 minutes, 5 times 60 plus 13. That's converting it. 5 times 60 is 300 plus 13. That will give us 313. Okay, so 313 seconds. So this is 313 seconds. So now if to divide that, in order to find the electrochemical equivalent, we have 3.2 divided by 50 times 313. Okay, so this is giving us 0.000245. Yeah, that's the answer, and it's going to be grams per coulomb. That's the unit. Quite easy, right? Quite easy. Now that leads us to question number 3. The first one says define an acid according to Lewis concept. Now I want to say this, that there are 3 concepts in the definition of acid. We have what we call the Arrhenius concept. We have what we call the Bronsted-Lowry concept. Then we have what we call the Lewis concept, the Lewis theory. Now I'm going to quickly run through them. Okay. Now an Arrhenius acid, for example, Arrhenius now. An Arrhenius defines an acid, or you can say Arrhenius acid is an acid that produces hydrogen ion as the only positive ion when dissolved in water. And Arrhenius base is a substance that produces hydroxide ion as the only negative ion when dissolved in water. Okay, that's for Arrhenius. Now for Bronsted-Lowry, Bronsted-Lowry defines an acid as a proton donor. We call it proton donor, and it defines a base as a proton acceptor. That's for the base. Okay, acid proton donor, base proton acceptor. Please remember that. Now in the case of Lewis defines an acid as electron deficient. Any electron deficient species is an acid. You can say electron deficient or electron acceptor. You can use deficient or acceptor. Okay, now that's very important for you to know. You can use deficient or acceptor. Then in the case of what will I call that now? In the case of the base is electron rich. Okay, I think the base is electron rich. Okay, you can call it electron rich or electron donor. Okay, electron rich or electron donor. That's very important for you to know. Okay, so those are the definitions. Now the next one says give one example of a Lewis acid. Electron rich, electron deficient, you can have aluminum chloride is electron deficient, iron 2 chloride, iron 3 chloride. These are examples of Lewis acids. Okay, even hydrogen ion is electron deficient, CH3 plus, but in an exam situation this would be better to indicate. Okay, very, very important. Now the next one says explain salting out of soap in soap preparation. Now of course the process of preparing soap is called saponification. I'm sure you know that. And saponification is when you react oil with sodium hydroxide, with caustic soda or potassium hydroxide or a base. You are going to produce soap. And so when the soap is produced, you will notice that the byproduct of soap is called glycerol. Okay, there is glycerol that is always produced. That means when oil, you're going to have something like this. When oil reacts with sodium hydroxide, you are going to get soap. Okay, then there is a byproduct. That byproduct is called glycerol. Now salting out now has to do with adding of salt in order to remove glycerol, or you can say adding of salt. Are you with me? Or you can say adding of salt in order to increase or reduce the solubility of the soap. adding of salt in order to reduce the solubility of the soap. That is very, very important for you to note. Okay, extremely very important for us to note. I'm trying to confirm something quickly. Okay, so that now leads us to the next one. It says state the reagent and condition for the following conversion. Now this compound, already seeing the triple bond, you should know that this is an ethyne, and the difference between this and this is that silver was, silver replaced hydrogen, silver replaced hydrogen. Now the reagent that happens, that makes this happen, is called ammoniacal silver nitrate. It's called ammoniacal silver nitrate solution. This reaction is one of the tests for alkynes, one of the tests that is used to differentiate alkynes from alkenes. Okay, since both alkynes and alkenes are unsaturated hydrocarbons, the only way you can differentiate them is either you use ammoniacal solution of silver nitrate or you use copper-1 chloride. Copper-1 chloride. That means CuCl. In the case of copper-1 chloride, this will be Cu, this will be Cu. And this guy here is silvery white in color. Going to be silvery white. But when copper is used, you are going to have brick red in color. That's going to be the color change. Okay, the next question says, what is the percentage abundance of an isotope? Now, the percentage abundance of an isotope is the amount of isotope, or amount of an isotope that is present, right? Is the amount of an isotope that is present in any combination of isotopes. Now, I want you to observe something. I want you to know something here, that, okay, that every element, most elements do not exist alone. Most elements exist as isotopes. And isotopy is a phenomenon whereby an element can have different mass numbers but the same atomic number. Okay, so the elements always exist as mixtures of isotopes. Okay, now the fraction of these mixtures is what we call percentage abundance. Okay, so the next question says, why does the element with the atomic number 18 not have an oxide? An element with the atomic number 18 does not have an oxide because 18 means that the configuration is very stable. It is completely filled. If I write the configuration for 18, I already mentioned something like that earlier. 2p6, 3s2, 3p6. All the electrons are completely filled. They are completely used up. So there is no one available for bonding. Okay? Excuse me. Now the next one says, okay. Now the next one says, explain why chlorine 1 oxide has a low melting point. Okay? Now explain why chlorine 1 oxide has a low melting point. Now I want to say this, that whenever you have a substance having a low melting point or a high melting point, either low or high, most likely has to do with van der Waals forces, because the intermolecular force responsible for boiling point is simply what we call the van der Waals forces. Are you with me? It's simply what we call the van der Waals forces. Okay, very, very, very important. So what that means, and van der Waals forces, okay, is usually affected by by molecular mass. So the higher the molecular mass of an atom, okay, the lower the van der Waals force. Okay, the lower the molecular mass, the higher the lower the molecular mass, the lower the van der Waals force. The higher the molecular mass, the higher the van der Waals force. So having low melting point simply means it has weak intermolecular force. That's the only explanation to that. Okay. Now the next one says describe a test to distinguish between concentrated HNO3 and concentrated H2SO4. Distinguish between concentrated HNO3 and concentrated H2NO4. Now there are many tests that can be used to distinguish them. That's very, very important. Okay, one of the tests can be reaction with copper. Okay, reaction with copper. For example, H2SO4 cannot react with copper. That means when you have H2SO4 plus copper, you are going to have no reaction. Now, but HNO3 can react with copper because HNO3 is not just an acid. Now, the reason why H2SO4 cannot react with copper is because copper cannot displace hydrogen in a chemical reaction. Okay, copper is lower than hydrogen in the electrochemical series, so cannot displace hydrogen in a chemical reaction. Now, but in the case of HNO3, the reason why this reaction is possible is because HNO3 is not only acting as an acid here, it is acting as an oxidizing agent. Okay, it is acting as an oxidizing agent. That's why you now have something like this. It now gives you something like this, then plus NO, then plus H2O, depending on if this is concentrated or dilute. Okay, that is one reaction. There are other reactions. Another one is that H2SO4 can be used as a dehydrating agent. It can react with sugar. When you have H2SO4 plus addition with any kind of sugar, what you will get is simply carbon. It chars it. To char it means it makes it a charcoal. Okay, but HNO3 cannot undergo this kind of reaction. Are you with me? Okay. Now another thing that can differentiate them is barium chloride. Barium chloride is a precipitating agent. When barium chloride reacts with H2SO4, you are going to have barium sulfate, BaSO4 plus HCl. Now this BaSO4 is a precipitate. Barium sulfate is not soluble, but that's not possible. You cannot precipitate with what is it called now? With HNO3. No, because even if it reacts, you are going to get barium nitrate, which is still soluble. So you can't precipitate with HNO3, but you can precipitate with H2SO4. So these are three different ways you can use to differentiate them in the laboratory. I hope that makes sense. Now the next question says, state two differences between an electrochemical cell and an electrolytic cell. There are many differences. One of the differences is that an electrochemical cell converts electrical energy to chemical energy. So electrical to chemical. Okay, but electrolytic cell converts chemical to electrical, like battery. Okay, so electrochemical cell converts electrical energy to chemical energy, but electrolytic cell converts chemical energy to electrical energy. That's number one. Then the second difference is that in electrochemical cell, anode is positive, but in an electrolytic cell, anode is negative. Are you seeing that? Then another difference, in an electrochemical cell there is no salt bridge. You don't see anything like salt bridge, but in an electrolytic cell there is salt bridge. Are you saying that? In an electrolytic cell there is salt bridge, but in an electrochemical cell there is no salt bridge. Again, another difference is that in an chemical cell, cathode is negative, and in an electrolytic cell, cathode is positive. Very interesting. Okay, very interesting. And if you are asked to find similarities, there are some similarities. For example, one of the similarities is that in both of them, oxidation occurs at the anode, reduction occurs at the cathode. So whether it is electrochemical cell or electrolytic cell, oxidation occurs at the anode, reduction occurs at the cathode. And that's the same thing with another difference is that both of them have anode, both of them have cathode, both of them uses electrolyte, and all of that. Now this says, how does the trend of ionization energy affect the reactivity of group 1 element? Now remember, we said that ionization energy is the energy required to remove a valence electron from an atom. And I also said that generally speaking, ionization energy increases across the period. Ionization energy increases across the period but decreases down the group. That means as you go down the group, lithium has 1 shell, sodium has 2 shells, potassium has 4 shells, okay, hydrogen has 1, lithium 2, sodium 3, potassium 4, and it keeps going. You notice that it becomes easy to knock off as you go down the group, knock off the valence electron. And the more easy it is to knock off valence electron, the more reactive it is. That means the ionization energy, okay, decreases down the group, decreases with increase in reactivity. Or we are going to say reactivity increases with decrease in ionization energy. That means the lower the ionization energy, the more the reactivity. That's why potassium is more reactive than sodium, sodium is more reactive than lithium, lithium is more reactive than hydrogen. The simple reason is because potassium has the lowest ionization energy, the lowest of them all. It can easily give out electron. That's what that means. Very easy to give out electron, making it very reactive, okay, as a metal. Now the next question says, define the term molecular formula. Molecular formula is the actual formula of a compound. Unlike empirical formula is the simplest formula of a compound, but molecular formula is the actual formula of a compound. Okay. Now the next question says, state which of the gases, hydrogen and ammonia, would deviate from the ideal behavior and give reasons for the stated answer. Now that is very, 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 very important. Okay. Now, and the question is, and the reason is that ammonia will deviate more. Ammonia will deviate more. The reason why ammonia is going to deviate more is because it has larger volume, okay, and also has stronger intermolecular force. Are you with me? Okay. And if you remember one of the laws of, I mentioned ammonia. If you remember the laws of kinetic theory of gases, okay, ideal gases, one of the things we said about ideal gases is that the volume of the gas is negligible compared to the volume of the container. Then the second law, again, another one again, is that the molecular attraction between the gas molecule is also negligible. So to deviate from ideal behavior means that your volume is a bit bigger. That's a deviation already. And also the intermolecular attraction is stronger. That's also another deviation. And somebody may be asking, how do you know the intermolecular attraction of this is stronger than this? It's because of hydrogen bonding. Hydrogen bonding provides the strongest intermolecular force between covalent molecules. And hydrogen bonding happens anytime you see hydrogen attached to fluorine, attached to oxygen, or attached to nitrogen. This is the strongest, they have the strongest intermolecular forces whenever you see hydrogen attached to fluorine or oxygen or nitrogen. And that's also what is responsible for their higher boiling point. Please note that. Very, very important. Okay, so that leads us to another question. Now this one says, state 2 conditions used in Haber process. Okay, the first condition is the presence of a catalyst. You need catalyst, ion catalyst. Haber process is the production of ammonia. Okay, nitrogen plus this will give us ammonia, NH3. And one of the conditions is that there has to be a catalyst, right? Okay, and the second condition is that it has to take place in the presence of high pressure and high temperature. That's, very important. Now the next one says, explain briefly the effect of increasing pressure on the rate of reaction in the Haber process. Now remember that the Haber process is a reversible reaction. And anytime you increase pressure in a reversible reaction, these are all gases. You can make here gases. Whenever you increase in pressure will always favor the side that has the lowest number of moles. What I mean is that here, look out for my video when I taught equilibrium. Okay, so the total number of moles here is 2 moles, and the total number of moles here is 4 moles. So if I increase the pressure of this system, is going to favor the forward reaction, because the forward reaction has only 2 moles, so it's going to favor forward reaction. Okay, now the next one says a mixture of nitrogen 4 oxide and oxygen is bubbled into warm water to produce triazonitrate 5. Write a balanced chemical equation for this. Ooh, okay, you have NO2, you have O2, then you have water, H2O. You're going to get HNO3, and probably that is going to be 2, and this is 2. I think the equation is balanced. Nitrogen is 2, nitrogen is 2, hydrogen is 2, hydrogen is 2, oxygen is 4 plus 2, 6, 6 plus 1, 7. So I think if I put half here, makes it balance, makes it 6. So generally, if I multiply by 2, this will be 4 NO2 plus O2 plus 2 H2O will give me 4 HNO3. Okay, so this gives the balanced equation. Quite easy, right? Okay. Using the balanced equation only, explain what would happen if nitrogen 4 oxide is bubbled into warm water. Using a balanced chemical equation only, explain what will happen if if only nitrogen 4 oxide is bubbled into water, you are going to produce 2 types of acid. Nitrogen 4 oxide is the only acidic oxide that dissolves in water to produce 2 types of acid. You are going to get HNO3 plus HNO2. This is what you are going to get. Okay, HNO3, and this is a balanced equation. Nitrogen is 2, nitrogen is 2, hydrogen is 2, hydrogen is 2, oxygen is 4 plus 1, 4 plus 1, 5. So that is for that one. Now the next one says compare the gases evolved when triazonitrate 5 decompose under each of the following properties. Okay, under each of the following properties. Compare the gases evolved when triazonitrate 5 decompose under each of the following properties. Okay, now when HNO3 decomposes, you are meant to get water, and you are going to get back water, oxygen, and NO2. Okay, so in the case of under the following properties, in the case of pH, water is neutral, oxygen is neutral, NO2 is acidic, so it has a lower pH less than 7. Solubility in water, of course water is water, NO2 is soluble in water, but O2 is sparingly soluble in water. Reaction with carbon 2 oxide, oxygen can of course react with carbon 2 oxide. CO plus carbon 2 oxide will give you carbon 4 oxide. Water can react with carbon 2 oxide, but actually it's supposed to be steam. Okay, not just water, steam. If this is steam, then it can do business with carbon 2 oxide, which actually is not really that visible. Then NO2 does not react. Okay, so these are the comparison. Very easy, right? Quite easy. Wow. Okay, I might need to make a correction here that NO2 also reacts with CO to produce NO plus CO2. Okay, to get that, but that's by the way. Now the next one says name 2 oxides of sulfur. Okay, we have sulfur 4 oxide, SO4. We have sulfur 6 oxide, SO4. Sorry, SO3. So these are the 2 different oxides of sulfur. Now the next one says write the balanced equation for the reaction between each of the named oxides, sulfur 4 oxide and sulfur 6 oxide and water. Okay, sulfur 4 oxide reacting with water should give us H2SO3, but sulfur 4 oxide reacting with water should give us H2SO4. Okay, yeah. Then the next one says, name one calcium compound A used to dry ammonia gas. Calcium oxide is what is specifically used for ammonia gas. Used for the manufacture of cement, calcium carbonate is used for the manufacture of cement. Causes hard water. For temporal hardness, you have calcium hydrogen carbonate. This is for temporal hardness. For permanent hardness, you have something like calcium sulfate. Okay? Then the other one says, name one calcium compound. Well, I can say calcium chloride. Calcium chloride. Yeah, this one is calcium hydrogen triisobicarbonate 4. This one is calcium tetraoxosulfate 6, and so on and so forth. Okay. I'm going to stop here. I'm going to continue. We have just one more question, one or two more questions. I will continue that in another video. Thank you very much. See you in my next video.